Day 28, projectile motion, kinematics, question number 25. This is actually not an acceleration problem, it's a uniform velocity problem, so really the only equation you'll be using in this one is V average equals displacement over time. And it's a vector problem. Basically it's a vector component problem. The ball is going downstream with the river at 1 meter per second. The person, the swimmer, is going to jump in and swim toward the ball, but they'll be carried downstream. Basically the path of the person relative to the shore will be diagonal. So I'll just kind of sketch it on the diagram. Once the person jumps in, they'll have a path that goes something like this and catch the ball downstream. But bottom line, if you draw the vector components for the velocity of the person, you have the 1.2, this is overhead view, this particular diagram I drew here, 1.2 meters per second across the stream, it could be north, and then 1.1 meter per second downstream. But bottom line is, this person, if I draw a vector diagram, there's my 1.2 meters per second, and then my 1.0 meters per second. The net resulting velocity of the person, I'll draw that in blue, is there. And you can Pythagorize that to get r, which will be slightly more than 1.2. So that'll be the resulting speed of the person relative to the shore. You could also get the direction of this motion by using tangents or sine or cosine of that angle right there, and the other angle would be the complement of that next to it. But bottom line is, that's the vector diagram for the velocities. That's the velocity vector diagram. The displacement vector diagram will have the same angles. Bottom line is, the person will be carried downstream a certain distance. We don't know what it is yet, but we do know that to get to the ball, the person has to go 50 meters, I believe. That's how far out the ball is sideways. So the displacement vector diagram, 50 meters there, and if you complete the diagram, there'll be, well, we'll call it M. Doesn't really matter what you call it. I want to call it R again, but it's the resultant of those two components of displacement. But we do know that this angle over here, and there's different ways of doing this problem, but this angle right here is the same as the angle for the velocity diagram. So once you know theta from the velocity diagram, you also know theta for the displacement diagram, and then using sines and cosines you can figure out how far downstream you go, and you could figure out the total displacement, the vector M in this diagram. So that's all the theory. I'll do one more part of this problem. Bottom line is, and there's different ways to approach it, essentially the first step in a problem will be, how long does it take the person to reach the ball? Well, that's all you got to worry about is the horizontal, or the 1.2 meter per second component. That's your velocity. If I go back up to the equation up here in the upper right, you got 1.2 meters per second equals, you're going to cover 50 meters in that particular time. And that'll tell you the time it takes you to get to the ball. And I don't know what that is. It's like 30 or 40 seconds. But then you can figure out how far downstream the ball goes in that time by using the same equation, and everything falls out from there.